Okay. So as usual, before starting, odds and ends. First off, problem set 1 was actually due just now, so hopefully you did it. I will put up a second problem set probably later today. About the scores, some of you wondered, you didn't do well, did well. You know, finally, working on the problem sets because the purpose of the problem sets is to have you struggle through the questions and learn from the experience. That is, being forced maybe to go back and review things or read things or think about things or talk about them with your friends and stuff. It's a learning process in the act of trying to complete these questions. That's different from the exams where you have far fewer resources during the exam, and hopefully then it's already in your head and you already understand it when you approach the exam. That's not at all the case for the problem sets. It's to work through them. If you don't face these questions yourself and struggle with them yourself, it's very hard to learn some of these concepts, particularly ones that go against your intuition. For example, these ones relating to acceleration versus velocity and inertia. It's just so easy to think that forces cause velocity, that pushing on something makes it move. It's not the case. Pushing on something makes its movement change, that is, its velocity changes, but the movement itself is dominated by inertia. Okay, so average scores historically on homeworks have been in sort of the 80 range, 80%. And I expect that to be very similar this go round. So if you're doing 80 and above, or great. If you're down in the 50% right and stuff like that, work on understanding the stuff better. It's sort of mostly a lot of heads-up aspect to it, pointing out things you don't understand well, learn from the mistakes. Any questions about the homework stuff? Yeah. Yeah, I'm going to be super lenient with this first homework assignment. So this one, your raw score, I'm not going to put the raw scores into the final calculation of grades. It's just too messy. This related to this, Orion. My current thinking with Orion is it turns out you guys can do Orion without me assigning it. And I think I can see that you're doing it. I haven't gone carefully to look for this. Again, I'm still learning. My current thinking is that it's better just to have you guys play with Orion and learn from the questions. Just do them without the pressure of the grading process. The grading, it turns out, is much more complicated than I expected. It involves time. It involves the scoring. It involves time. It involves which of the little icons about your confidence. That seems to go into the scoring. It's not a straightforward process at all. I just got back the information about it, and the email is this long, and I haven't read it yet in detail. That's not my plan. I want you guys just to basically dealing with these questions is the value. It's not about the score. So for the second chapter this week, you'll play with the Orion, which you can do just by clicking on that tab, and then you can do the diagnostic or not at your whim. And I think that from now on the diagnostics are more instructive than the first diagnostic. The one associated with chapter 1 is entirely quantitative and very hard, and therefore not very valuable, particularly to people just starting out. I mean, it's just like getting hit with a mallet. So from here on, they're better. So doing the diagnostic may be valuable to you. Doing the Orion will certainly be valuable to you. It will just keep telling you, pointing out things you understand well and things you don't understand well. Is that okay? So do the Orion even if I don't assign it. I will. The participation component of the grade, I'll do my best to figure out how to get that done properly. I will reward people who do the Orion, and I will not reward people who blow it off. Okay? Last thing is you guys are asking lots of questions in class, and that is great. It's been a while since I had a very interactive class, and like you guys should be proud of yourselves for doing it. Otherwise there's no point in me giving a live class. And education will evolve eventually. It's very slow to change. And finally, if there's no interaction in the class, it might as well be replaced with a video. That's not quite, it's more complex than that. But anyway, so thank you. You guys are good. All right, any other questions about the stuff we've done, physics things in the past? Stuff you're still wondering about? Yeah. The difference between positive and negative work. And the word positive is implicit in work. I told you that. That's a convention. So that if I do positive work, I often will just simply say I do work. To do positive work, you push on something, and it has to move in the direction of your push, or approximately the direction of your push. But in fact, the only part that counts is its movement in the direction of the push. So if I push up on this, and it moves up, and I am pushing up on it, and it is moving up, I do positive work on it, or just equivalently, I do work on it. So far, everybody okay? If I push up on it, and it moves downward, then I do negative work on it. And I'll do that right now. I will lower it slowly and uniformly, steady speed. If you were me, you would know that I'm still pushing up on it. I pushed up on it the whole way, and that's important. And yet it moved downward, opposite my push. That's a negative amount of work, because the force and the direction were in opposite directions. Is that okay with people? So when I push up, but it moves down, I'm doing a negative amount of work. If I push up and it moves down at an angle, I'm still doing negative work. To the extent that it moves sideways, that doesn't count, because my push was up. Movement at right angles to my push doesn't count, but the movement downward does. Is that okay with everybody? Yeah. Super. If it were attached to a springy cord, and instead of pushing up as it came down, I were pulling down as it came down, then I would be doing positive work on it. You're right. And so one thing that confused people, and I've talked to them about when I was with the bowling ball, was the lowering process. They talk about me pulling the ball down. I wasn't pulling the ball down any more than I'm pulling the weight down now. I'm still pushing up on it. What I'm looking around for is something that I can, with some I've got more balloons. If I push it up, I do positive work on it. If I lower it while pushing up, I do negative work on it. But I can do positive work on it on the way down. I can either pull it down from above, whether it's got a spring on it or not. I can pull instead of push. And if I do, weight will be pulling it down, and I will be pulling it down. What will happen to the balloon? Will it accelerate? How many think it will accelerate? Yes? Correct. Will it accelerate downward? How many think yes? Will it accelerate downward faster than gravity alone would make it accelerate? How about that? The answer is yes. When you throw something down, it's gone. Did I get you guys? Oh, sorry. Okay. If I remembered, okay, aside, always dangerous because I waste time. You don't care a lot. If I remember to do this, I've got a cannon that I made that it uses vacuum to fire stuff. We take the air out. We will talk about fluids, the behavior of fluids, including air, which is a gas, and water, which is a liquid. They both lump together in their category of things known as fluids that take the shape of their container. I've got a cannon where you take the air out of a chamber. It happens to be a PVC pipe. And then you remove the cap on one end, and air rushes in to replace it. And whatever you put at that end of the pipe inside, like a ball or an apple, is pushed forward by this inrushing air. And when it reaches the other end, which pulls free because of a spring, when it reaches the other end, it's traveling quite fast. If it's a light enough object, it's traveling 250 miles an hour. If it's an apple, it's only traveling 150. We clocked it. And when it hit the wall, we haven't done this for a couple of years for this reason. When the apple hit the wall at 150 miles an hour, this half of the class was decorated in applesauce. So I'll try to do the demonstration, but not with an apple. Aside is over. Yeah, I don't know if they ask you whether that's okay. Back to the issue at hand is if you push something downward, so the only force acting on it is your push downward and its weight, two forces, it will accelerate downward faster than gravity alone would do. And that situation is not uncommon. And to give you a preview, that is what happens in a loop-the-loop on a roller coaster. When you go over the loop of the roller coaster, presumably a lot of you have done this, and if you've paid attention, except with your eyes, you can't tell the moment when you're at the top upside down. It's very difficult to tell. And a part of the reason for that is that in that curve, remember, any change in velocity is an acceleration. When you're going in a curve like this, you're accelerating. In fact, which direction are you accelerating? Downward. You're going from an upwardish velocity to a downwardish. You're accelerating downward. How fast are you accelerating downward? Faster than gravity alone would make you do it. So you are being pushed down by the roller coaster, and you feel that downward push. You feel it. You feel your own inertia, and we'll talk about that too, trying to keep you going somewhat straight. Gravity alone doesn't help it. You're actually shoved downward, and you feel shoved downward. As a result, you are upside down, feeling shoved downward. That sure feels like the whole world is turned upside down, and you're experiencing gravity towards the sky. And so we'll flesh that all out. But it means that things like, this is a terrible object to be doing it with. I usually do it with a book. But I'm not holding it. I'm just, in this motion, going over the top like that, I'm actually pushing down on it the whole time. So it's accelerating downward. This is a much less dramatic downward acceleration than me throwing the balloon into the floor. But the physics is very similar. It's a downward push. I'm still pushing it toward the ground, and it's accelerating down like crazy. Is that okay? So to finish the question about the work, when I threw that water balloon into the ground, I was pushing down on it as it moved downward. I was doing work on it. And that's how it got to be going so fast, because I was adding energy to it. It was already converting its gravitational potential energy into kinetic energy as it descended. That's what falling things do. They turn their stored energy and gravitational potential energy into energy of motion. And I added even more. As a result, by the time it hit the ground, it was traveling very fast, much faster than it would if it was falling alone and splat. Is that okay? Any questions? Yeah. Yep. On the slide. So the question is when a ball is rolling down a slide, its acceleration varies. And this is one of the problems you encountered. When you drop a ball, it experiences only one force, its weight, and it accelerates downward, 9.8 meters per second. When you put a ball on a ramp, and ramp in my mind, and as I use the word in this course in general, is a uniformly sloping thing. So when you do that, the ball experiences a downhill force, a ramp force, that is weaker than its weight, right? And it depends on the steepness of the ramp. It still imitates weight very nicely because ultimately it originates in weight. It has to do with the weight of the object. And it imitates weight in the sense that the more massive the ball is, the more weight it has, the more ramp force it summons. And they scale perfectly together. So you double the mass, you double this ramp force. And consequently, the balls all roll down the ramp at the same rate. Big balls, little balls, the works. It's a little more complicated because there's a rolling motion, which is messy. We'll get there, sort of. Is that okay so far? The steepness of the ramp matters. And on things like the slide that I described in that question, or slide, many water slides. Pick a slide. Those of you who've ridden on a water slide at an amusement park, the slope changes. And so it's not one ramp, it's a variety pack. And the acceleration varies with steepness and gets bigger with steepness. So the steepest part of any given complicated slide, that's where you're accelerating the fastest, because that's where you're experiencing the biggest ramp force. And that's true of slides, it's true of roller coasters too. So you've had lots of experiences of accelerating on strange, complicated ramps. And the fastest acceleration, and if you think back to this or watch it next time you go riding one of these, you will notice that you're accelerating the fastest, neglecting air and friction and stuff. You're accelerating fastest on the steepest parts. Is that okay? Other questions? Yeah. Okay. So here's a question that many of you have asked me this too. Denting the wall with a hammer. Did you do positive work or not? First off, as a preface, asking a question perfectly clearly is a very complicated process because it often involves 1,000 caveats and all sorts of neglecting air resistance. And I can make a question that looks this long. It's very simple. It's this long to be legally correct, and sometimes I leave out the pieces. And sometimes that's okay, and sometimes it's a mistake. So why does this fit into this current story? When I talked about someone's inability, my inability to do work on a wall, implicit in that is the assumption that I cannot move the wall at all. That's an overstatement. It's oversimplification. Walls aren't perfectly rigid. Like sidewalks, they dent a little when you push on them. So if I include the statement, an immovable wall, which makes it unrealistic. Okay, this is science fiction, but it's for a good cause. Then I can't do work on it at all. Is that okay? A realistic wall does dent. If you look over there at that wall, it's got some dents in it. And that piece of paper there, I think, is covering dents. I think, I've shot a lot of stuff into that too, and I'm not the only person who does wacky stuff in that room. So when you hit a wall with a hammer and dent it, I'm actually implicit in that is that the wall does have the ability to move in the direction of forces, and then you can do work on it. So I will try, for example, in test questions, to include the crucial caveats like neglecting air resistance, because if you include air resistance, the answer changes, right? And that's not what I'm not trying to test you on your detailed understanding. For example, right now, air resistance, I brought it up a couple times, but it's not the story. I'm trying to elucidate really the simple parts of physics. Leave the air resistance out. It's really interesting, but it's for another day. And I left the denting ability out of the wall when I first bring it up. Now we can start bringing in the idea that, yeah, things do dent. Is that okay? Other questions? All right. So with seesaws, the purpose of seesaws, and I know from sad and long experience, I can get lost in this topic way too long, and therefore will abbreviate it as best I can because it's useful to us, but not super useful. Seesaws is a story of rotation. And up until now, I've talked about motion where you're going somewhere. You have a velocity that takes you from position here to position there, and maybe you're accelerating so your velocity is changing with time. That's a type of motion known as translational motion. That's the sort of the formal name for it, where you're going from place to place. It's called translation. Brings to mind all kinds of language things to me, but it is the right word. Seesaws don't go anywhere. They sit on the playground, becoming rarer and rarer. It's really sad. There is no seesaw left in Charlottesville, Virginia except maybe at people's homes. There's one in the attic. I got one, but it's a pain. Forget it. So hopefully you've all, at least you can picture what a seesaw is. You know, it sits in the middle of a medieval castle, the last time one was ever seen. I figure it's either because kids get bored easily these days and they want a seesaw in an app, or it's because the lawyers got into the story. And seesaw is actually, you can get hurt on a seesaw. The classic way to get hurt, and there's good physics in this, is to have two kids on a seesaw, and one kid is up in the air. At the moment the kid down here decides, you know, here's the ice cream truck coming, jumps off and heads off for the ice cream truck, bam, right? And this kid here bites his or her tongue badly and goes and gets stitches. So anyway, the seesaw I have in mind is one where two kids sit on it and they rock it back and forth. It's a rotational motion. They're not going anywhere overall. They're just teetering it back and forth about a pivot. Still familiar to people? Good enough. Okay. So, since this is then the story of rotational motion and an introduction to the sort of the language and central issues of rotation, here's a rotational problem. You and another child, and the child is half your height. So, here's you, nice and tall, kid, okay? You both plant your feet, lean out over a pool, because I don't want you falling on asphalt or something like that and suing me. And you both, at the same moment, you're at the same angle, same moment, you let go of whatever's holding you up at an angle, and you topple over into the pool. Who hits the water first? You, the tall person, or the kid, the short person? Okay, the question? How many think that you hit first? How many think the kid hits first? Vast majority for kid hits first. Okay, I'll show you. Right? You can root for your favorite person. I'll let them over. Ready? Get set. There's no competition. Kid hits way before the short kid hits way before the tall person. And the physics behind that, as we'll see, is it has to do with the equivalent of force in the context of rotation, influence known not as force but as torque. The torque on the two of you is different, the twist, and also the equivalent of mass in the rotational context, a quantity known officially as moment of inertia, which is a horribly complicated name that I abbreviate. I call it rotational mass, because that sure just gets to the heart of the matter. It's a battle between the influence that causes rotation to speed up and the influence that impedes it, that fights it. So the equivalent of force to mass, in this case, it's torque to rotational mass. And it turns out for the little kid, the torque to mass, to rotational mass ratio is much higher than it is for the tall kid. And therefore, the short kid undergoes a much faster rotational equivalent of acceleration, which is known as angular acceleration, and outpaces the tall kid and gets there first. Is that okay? It's mostly a preview of things I'm going to talk about in a second. But you can see it in action. This has consequences. Tall things tip over very slowly. If you ever cut down a tree, very tall trees take ages to rotate over, just like, you know, it's like the equivalent of the world's tallest kid here. And often they break on the way in the process of tipping over for interesting reasons. There's a lot of internal stress on things that are tipping over. And the public service announcement then of this story, and a lot of my questions are sort of secretly public service announcements. I'm trying to give you some insight into how your world works in ways that will be helpful to you. Tall trees that are not structurally sound, they've been dead for 20 years and you're cutting them over, and they will break easily if they have internal stresses. Be really careful tipping those babies over, because they fall very slowly as you just saw, and they tend to have so much stress inside that they fall apart. And the parts, once they've fallen apart, don't rotate anymore. They drop, they fall. And so you can have this stuff come raining down on you. You can be cutting a tree and watch it go, timber, and then all of a sudden the top portion doesn't keep timbering. It breaks and comes right down on you. And the public service announcement, Pat, is don't let that happen to you. I mean, it's not actually, ha, 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 and I say lots of ha, ha, ha things that are not funny. People get seriously injured by this. I'm not going to check to see whether any of you have it, but it's, I know, we've got a family friend who got creamed this way. He's been in a wheelchair for 20 years. Okay? So, some observations about seesaws. A balanced seesaw, and the word balanced itself is an interesting word and suggests something important. It rocks back and forth easily. If you've had the opportunity to ride a seesaw, and you get it balanced, it goes back and forth with great ease. Interesting things are involved, but it's not hard to tip it back and forth. Equal-weighted children can balance a seesaw by sitting at equal distances from the pivot. If they're not equal weight, they have to adjust. So if you've got a heavy kid and a light kid, they can't sit on the seats together, opposite ends equally. The heavy kid's going to spend all the time on the ground. The heavy kid, it turns out, has to sort of move in towards the pivot for useful reasons or important reasons. Okay, what else? The closer the kids sit to the pivot, the easier it is to get the whole thing teetering back and forth. So there is a rotational mass issue here that as you put the kids out farther from the pivot, the rotational mass, its resistance to changing its motion gets worse. And if you've noticed, one thing that was always fun to do on a seesaw when they existed was to stand right over the pivot, no kids, and you could just teeter it back and forth with your own feet. And you could make it go up and down like crazy. So having everything right there in the middle makes the rotational effects very easy. All right, I got my usual bunch of questions to go through, and I will. And the first one is, what the heck? Well, how does a balanced seesaw move? Which is in part the story of what the heck is a balanced seesaw. So the balanced seesaw, how does it move? And my short answer is it moves at a constant rotational speed about a fixed axis in space. So it already has some words in there that I got to deal with. But I can show you a balanced seesaw. This is one. So there's the bar. I've kind of gotten rid of the ground, but it's sitting, there's the pivot, there's the seesaw. And a balanced seesaw, you might think that it's horizontal. It's not, it's very close to balance, it's not quite perfect. You might think it's horizontal, but that's not the only possibility. It could also be tilted like this. And it can also be turning steadily about a fixed axis, in this case, that pivot bar. But, so, the point of this whole thing is to show you that a balanced seesaw exhibits a form of inertia. Remember, for the inertias we've been dealing with in the past, inertia points out that left to itself, an object at rest stays at rest, an object at rest in a different place stays at rest, and an object that's moving continues moving in a straight line at a steady pace. This is the rotational equivalent of that story. A balanced seesaw, which is basically an inertial seesaw, can be at rest, like in this arrangement, which we'll call an angular position as opposed to position. It can be at rest like this, which is a different angular position, but it's sitting there. Or it can be moving steadily. And that steady motion like that is analogous to the velocity, this constant velocity of an inertial object that's translating. So an inertial object that's translating has constant velocity, right? We've done that a zillion times. It's experiencing no overall force, and it just keeps doing what it was doing, moving at constant velocity. This is the rotational equivalent of it. It's experiencing no overall influence that affects rotation, and as a result, it moves at constant, well, not velocity, because velocity is about getting somewhere. It's moving at constant angular or rotational velocity. There's a little friction in it, but basically if I get it started, during which time it's not inertial, now it's inertial, balanced being inertial, now it just keeps doing what it was doing. It happens to be a motion. It's a rotational motion. It just keeps going. Rotational inertia. You okay? So the physical quantities to bring up then. Just as I had 5 physical quantities for translational motion. You're okay with the word translational motion? Translational being going somewhere. I had 5 quantities. Remember, position, which is where you are. And velocity, which is how your position is changing with time. And acceleration, which is how your velocity is changing with time. That's 3. I then had forces, which cause acceleration, and mass, which resists it. And that's sort of a complete story. Well, hopefully you're at least comfortable with that. This is the same story now, but I got 5 different quantities. The quantities that deal with rotation. So instead of having position and then its rate of change being velocity and the rate of change of velocity being acceleration, I've got the rotational versions. So I've got angular position, which is how something is oriented. More about that in a minute. And angular velocity, which is how the angular position is changing with time. And in a minute, I'm going to have angular acceleration, which is how the angular velocity is changing with time. And the influence that's analogous to force that causes acceleration, in rotation, it's called torque, and it causes angular acceleration. So a torque is a fancy name for a twist. So when you visualize, grab the doorknob of a door, top and bottom with your fingers, and give it a nice turn, you're not pushing it somewhere. You're not trying to make the doorknob head up, accelerate up. You're trying to make it begin rotating for the first time. And so that is a torque, spelled T-O-R-Q-U-E. You encounter this word from time to time, and car engines maybe come out with torque, or torque wrenches. If you go to the hardware store, you can buy wrenches that are called torque wrenches, because wrenches, which are they're levers that grab onto a nut or bolt and twist it. That's a torque. That twist from a wrench is a torque, and a torque wrench is one that tells you how hard it's twisting. So it's useful because if you twist too little, the nut or bolt can come loose. If you twist too much, you can break the nut or bolt. So the torque wrench, some situations, like how tightly you put on the lug nuts on the wheel of your car, there's actually a specification that I never pay any attention to. I have no idea what it is, of how hard you're supposed to twist those nuts to hold your wheel of your car on. If you go too little, you're going to have a wobbly wheel eventually. If you go too hard, you break off the nut. Okay. All right. So angular position, angular velocity, torque. Questions so far? All right. Some issues relating to these. All 3 of them are vector quantities. They have a direction to them. And the direction is not exactly intuitive or straightforward. Velocity's direction is really pretty easy to see, right? If I'm heading this way, the direction of my velocity is this way. Life is simple. Ain't that cute? For things like rotation, what's the direction of that that angular velocity, which is describing how its angular position is changing with time, is interesting. Okay, this sure looks very similar, but it's the other way. How do we, what's the direction here? So here's how the direction works for these rotationally things. The direction points along the axis, the rotisserie axis about which whatever rotational thing you're dealing with is taking place. For example, I'm going to, and this is always dangerous for me because eventually I get dizzy and it's, sorry. When I start falling over, it's life. I'm rotating, therefore whatever my angular position is changing with time, and I'm rotating about a particular axis, which happens, if you made me a rotisserie chicken, the rotisserie stick would be going right through to the ground, right? That's the axis I'm spinning around by, I'm going to stop. So the direction of my rotation, as I just showed you, is related to that up-down direction. That's as opposed to, and I can't do this for more than a moment, right? This rotation, right? Now the axis is toward you, away from you, as I rotate like that, okay? So by convention, the axis of rotation about which some rotational phenomena is taking place, that is the direction of rotation. This applies to angular position as well. I should just point out a little bit about angular position. It's not nearly as useful to physicists as its rate of change, which is angular velocity. But angular position is things like, I'm facing forward, that's one position, angular position. I'm facing to your right, that's a different one. I'm facing the floor, yet another. And similar to what we did with position itself, I need a reference, and the reference is going to be, this is official position 0, angular position 0. Just as, remember, I had official position 0 being this point right here at the beginning of the semester. So this is official angular position 0, upright. And so my specific angular position at any given moment is my rotation away from position 0, angular position 0, such as this. This is easier. How did I get here from the 0? I was rotist, that is a verb, to rotist. I rotist like this, a quarter of a turn, measure it as you like. 90 degrees, for example, is a perfectly good way of measuring it. 90 degrees about a vertical axis, a vertical rotisserie axis. So here I am rotated. So my angular position right now is 90 degrees vertical. Is that okay so far? There's an ambiguity here. This is 90 degrees vertical, but so is this. 90 degrees vertical. Problem. Okay. How do you distinguish this from this? They both have the same angular rotation, which is the amount of the angular position, and the axis looks similar. Well, fortunately, any given linear axis has two directions along it. Up, in this case, and down. Two choices. We will assign one of them to this, and we'll assign the other one to this. And by convention, this one is called up, and this one is called down. You go like, how the heck did he know? It's a choice. It's an arbitrary choice. It's a choice made years ago, and we all agree on it. And knowing the choice is interesting. I won't hold you accountable for it, but you might as well see it at least once. You see that it's an arbitrary choice. We call one the other. It's like, shoes. Two shoes, they look pretty much the same, except one's mirror image of the other. Just like this is a mirror image of that in some respects. We call that one right, we call that one left. It's an arbitrary choice. It's the relationships between these two things actually are very close and very interesting, but long story. I'm not going to go there. All right. How do I know that the convention says this one is up? Turns out there's a rule. It's called the right-hand rule because it uses your right hand. And if you're left-handed, you still use your right hand. The right-hand rule says this, that if the rotation took place along the direction your fingers can bend, like this. Of your right hand, your thumb points in the direction of the rotation. If you use your left hand, you're in trouble. You get the reverse. But the right hand rule, and it was just an arbitrary choice, and it has this lovely artifact. We all have, well, most of us have right hands. Got to be politically correct here. And therefore, have this lovely tool we can use to identify. This is an up rotation by virtue of my fingers the fingers of my hand going in this direction with my thumb points up. And this is a down rotation. Is that okay? So this applies to all the rotational thingies. So if I start to spin like this, is this an up angular velocity or a down angular velocity? You tell me. It's up, right? There's my fingers. Up I go. And it is completely different from this. And that's going to be important. We'll see that in order for me to go from rotating up to rotating down, I have to undergo an enormous change in rotation. I have to undergo, my angular velocity changes dramatically, because direction matters, and I undergo a huge angular acceleration, and that is propelled by a big twist, big torque. And we'll play games with that soon, not today, but soon. All right, so this is the seesaw right now is rotating away from us, and now the seesaw is rotating toward us. That's its direction. And the faster it rotates, the bigger the angular velocity, the direction. If I go this now, it's still pointing toward you. The rotation direction is still toward you, but it's faster, bigger amount. Okay? So, a balanced seesaw, just make sure I finished that idea. A balanced seesaw is one that's experiencing no overall torque, no net torque, no net twist, and therefore is moving as inertia had in mind. So this is an inertial to the extent that it doesn't have friction. It does. And air resistance, too. If I could get rid of friction and air resistance, it would turn just absolutely steadily about a fixed axis in space, which is to say the direction of rotation is the same. The amount of the rotational, the rate of rotation is the same. It's a constant angular velocity. And that then gives us Newton's first law, not for translational motion, which was implicit in the name Newton's first law, but Newton's first law for rotational motion. It's just another observation that inertial things happen. And it's, it would be nice if it were as simple as Newton's first law. It's not quite. I'll come back to the waffle words in it in a second. But it's the idea that if you don't twist something, that the net torque on something is zero, it turns at constant angular velocity. It just keeps doing what it was doing. That would be lovely if it were true. It's not quite true. And the not quite true is, you have to limit it. It's only true for rigid objects. An object that can change shape can play games with its rotation. And the classic example, which I'll come to another day, is the ice skater. The ice skater spinning with her arms out, woo, and then she pulls her arms in. What happens to her? She goes faster. So she violates, she is no longer covered by Newton's first law of rotational motion because she's not rigid. She changes her shape. And when she does that, her angular velocity is no longer guaranteed to be constant. It can change, okay? The other waffle word that's in there is not wobbling. Objects that can wobble, like this mallet. Once again, he plays with fire, right? That kind of wacky motion is not covered by Newton's law of rotational motion. First law, all right? But if you have a rigid object and it's not wobbling, ball, for example, life is simple. Leave it alone, no net torque on it, it turns a constant angular velocity. That means that its rate of rotation is constant, its speed of rotation, and the axis about which it rotates is constant. And examples where this shows up for real is things like satellites. some fraction of the satellites that are put up there into nearly empty space are spinning. They're set spinning deliberately. It gives them certain advantages. And they set them up, they're spinning, this year, and they come back and visit them, say, 20 years later, and this has happened, and they're still spinning about the same axis at the same rate. It's just Newton's first law, beautifully illustrated, just keeps on going. Okay? All right. Why does the seesaw need a pivot? And it needs that because you really don't want it translating. The simplest thing for it to translate into doing is falling. It'll end up on the ground, and then it's boring. It's not much of a seesaw anymore. It's just a board on the ground to sit on. So the pivot separates rotational motion from translational motion and forbids translational motion. Now, objects frequently can do both. So, for example, if you throw a baton up, okay, so I wouldn't say I'm the world's worst baton twirler, because I'm sure there are other people that rival me. But if you throw a baton up, so it's spinning and I have a death wish today. So you throw it up so it's spinning. It's doing two things at once, unlike what I can do. And what is it doing? It is falling to some extent, like objects do when they have weight and nothing else. And it is rotating, which objects do because they like to do it. And this motion, although it looks complicated, is actually remarkably simple. The baton, or meter stick in this case, is rotating about its own natural pivot, a point that is known as its center of mass. It's pivoting about that. That is the natural center around which objects rotate. Freeing them from everything else. You take them to deep space, give them a spin, they will rotate about a point known as their center of mass. At the same time, that center of mass will travel in the arc of a falling object, as though it were as though all the mass of the object, the baton, were located at that point. And I'm realizing I'll dredge up videos of me throwing stuff on the lawn, and you can see that the rotation occurs around the thing being thrown. At the same time, that center of mass is just traveling beautifully in an arc of a falling object. The long and short and bottom line of this is that it's another case where complicated things can separate. We saw that a ball thrown in an arc separates into its vertical motion, which is falling, and its horizontal motion, which is coasting. In this case, it's a system that's separating into its translational motion, which is that of a falling object, while it's rotating, which is that of an inertial object doing what it was doing the whole way. The center of mass is approximately, I'm almost done, I'll just do one more tidbit. The center of mass is often very close to the center, the geometrical center of an object. For example, in a conventional ball, just an ordinary ball, it's pretty much center of the ball. If it's a baseball, of course, it's in the meat in the center of the ball. If it's a basketball, it's in the empty air space in the center of the ball. If it's this wacky ball, and I'll tell you in advance that this has got a water balloon basically inside on this end. So nearly all the mass of this ball is in my hand right now. This is the natural pivot for this ball, even though it looks symmetric somewhere else. And so if I throw this, I can throw it to you all, but it rotates weirdly because its translation motion is that of the arc of a falling ball around this point. This point's but its rotation is about that point too, and the physical ball is doing this wobbly thing around that. You can play with this effort. All right, we'll call it a day and finish up on Friday with seesaws.